Hello, today I will explain a fundamental concept in polymer physics, the Kuhn segment length. This term plays a critical role in describing the flexibility of polymer chains, which is key to understanding their mechanical and thermodynamic properties. This is a concept in single chain behavior where we discuss one of the most important factors that affect polymer chain behavior, the length. In reality, the polymer chain is not all spread out into a single line, and the chain doesn't behave like a single flexible string. Rather, it has stiffness due to intramolecular interactions and molecular constraints. And the chains will randomly coil up. This leads to a question: what is the length of the polymer chain actually, and how can we calculate them? There are two ways to calculate the length. We can calculate the contour length, which is the total length of this chain along its backbone, or we can calculate the end-to-end distance of the polymer chain. In this case, we investigate in different ways that can be used to simplify calculation of the contour length of the polymer. In general, there are three models to calculate the contour length. The first one is the simplest and the most ideal case. It is called the freely jointed model. In this case, it is assumed that all bonds can rotate and fold freely and have no constraint on bond angles or rotations. However, this is not realistic. If we consider more realistic cases, we will have the valence angle model that takes into account the bond angles and hybridization, because repulsions in chemical components can restrict how a polymer folds up. Also, there is the rotational isomeric state theory, where bond rotations are taken into account. Because of the extra constraints that the two models consider, the valence angle model and the isomeric model will give a more precise calculation. However, this also leads to making the calculation for the valence angle model and the isomeric state model relatively complicated. The Kuhn segment length, denoted as B, is a way to simplify this complexity. We can imagine trying to bend a relatively rigid coil. If the two hands hold up too close together, the coil is not too likely to bend. This mimics the fail to freely jointed model in polymer behavior, because the coil is not freely rotated. The idea behind Kuhn segment length is to separate the polymer into long enough segments so that the segment can represent the length of an equivalent hypothetical segment that behaves like a freely jointed chain. In other words, it is as if the polymer were made up of a straight, non-flexible rods of length B connected by freely jointed joints. For a polymer of contour length L, the number of Kuhn segments is given by n equals to L divided by B. The Kuhn segment length B can also be represented as C infinity times L, where C is the stiffness of the chain and L is the bond length. This formula gives us a very intuitive way to think about the relation of Kuhn segment length and the polymer stiffness. As the Kuhn segment length increases, the stiffness of the chain also increases. This makes sense intuitively as we think back on the coil example. The longer the hands have to hold to freely bend the coil, it probably means that the coil is harder to manipulate, and thus we can say it is stiffer. To summarize, Kuhn segment length is critical in multiple polymer science topics, as it helps us to understand the chain behavior under different conditions such as stretching, compression, or flow. It also significantly simplifies the calculation and helps to predict the physical properties and design materials for many applications, such as in plastics, textiles, and biotechnology. Thank you.